Well, my dear participants, now in my current talk, I am going to talk about pairs and then sum of squares, then fitting of LM, example, volume trees. So here I am going to extend these concepts for fitting simple linear regression model. The simple linear regression model is one in which there is only one predictor or input. The model for trees data with girth as input is volume is equal to beta naught plus beta 1 girth plus E. We fit this model using LM. Now see what we are doing, how we are writing this formula. Actually, here in the first argument of LM is the formula argument. And how this formula is written, it is, say for example, y is equal to beta naught into beta 1 plus x. Then it is written as y tilde modeled as. Then we don't write the coefficient of 1, or if we want to write the coefficient of beta naught, it is 1 plus coefficient of x is, coefficient of beta 1 is x, so we will write x and we will not write error. And normally this is equivalent to y tilde x because this intercept is by default it is taken into the model. So here the second argument is data, first argument is formula, second argument is data. Data is equal to t. This is same as LM volume girth and print. This is the print result. Here the y-intercept is minus 36.943 and girth is 5.06. So what is the interpretation of this result? Beta 1 here beta 1 hat is equal to beta 1 hat, this is the regression coefficient is 5.066. That means this is known as regression coefficient. So 1 for increase of 1 inch in girth, there is an increase in the response in the volume of 5.066 unit. So this is the interpretation of the regression coefficient. And here these are the residuals, minimum residual, these are E hats, minimum residual is minus 8.6 and maximum is 9.58 and first quartile of residual is minus 3.1 and median is 0.152 and third quartile is 3 point this thing. And then we are talking about the estimates, intercept and beta naught. Estimate of intercept is minus 36.943, is standard error is 3.351 and if we divide this 36 point this by standard error, it is t value. And the probability of this one I have already explained in my last lecture how these things are computed. And girth, the estimate of the regression coefficient of girth is 5.06 and standard error is 0.24. So if we divide this by this, it is 20.48 and probability greater than 20.48 is 2 into this thing. And this is the residual standard error. Residual standard error is nothing but actually this is sigma hat, and R square is nothing but actually it is SS due to regression divided by SS total. So actually R square measures proportion of variability explained by the model, and adjusted R square, it adjusts for the number of predictors, because one beauty of R square is that uh, not beauty, rather it is a problem with R square, is that as you increase the number of predictors, R square will increase, whereas adjusted R square, it adjusts for the number of predictors. And F statistic, actually F statistics is nothing but, if you want to test beta 1 is equal to 0 versus H1, beta 1 not equal to 0, to test this statistic, there is one t test. So here it is t, and if we make square of t, that becomes f test. So that f test is here. F test is here. Thus I will explain in the commands. I will explain in the commands also, like here, see, we run these results. So here, see, we have already explained what is the estimate, how we say, for example, 5.0659, this is the estimate of beta 1 divided by standard error of beta, and that is 0.2474. If we divide this, we get t value. So this is 20.47, this t value. Divide this by this, we get t value. And p value is nothing but probability greater than 20 in absolute sense. So it is this one. And see, residual standard error is nothing but it is the value of sigma hat with 29 degrees of freedom, and multiple R square is proportion of variability explained by the model. So it is 93% variability could be explained by the model, and adjusted R square, it adjusts for the number of predictors, and F statistic actually 1400. So I have already told you about how we can test beta 1 is equal to beta 1 is equal to, if we want to test beta 1 is equal to 0 versus beta 1 not equal to 0, it is t statistic, and square of t is nothing but f statistic. So here, if you make square of 20.47656, you make square, see, this is the 419.4, this is the F statistic 419.4. So these are the some of the interpretations of the R square and other values. We can get a lot of information from the fitted object M1 by using the following arguments. See, names M1, if you give the command names M1, it has a lot of information like coefficients, residuals, effects, rank, fitted values, assign, QR decomposition, DF dot residual, X levels, call, terms, model. Summary, name summary M1. Summary, it has call, terms, residuals, coefficients, alias, sigma, DF, and then DF degree of freedom, then R dot square, adjusted R square, F statistics, and COV unscaled. One can extract these using, say for example, M1, just I would like to go there. Say for example, we have fitted object and we can select M1, M1, C names, control 2, names M1. M1 is the fitted object. So we are getting these things. Suppose we use $M1 coefficient. These are the options, coefficients. So we can get regression coefficients. Similarly, if we are using M1 and we are writing residuals, we will get residuals corresponding each observation. So similarly, other information can be extracted. For example, to extract R squared, we have to use summary M1, and if we print names summary M1. See, these are the summaries: call, terms, residuals, coefficients, LES, sigma. Say for example, if we need the information about sigma, so summary M1, and we have to use dollar and we have to write sigma. So it will give the value of sigma. Similarly, if we want to know the degree of freedom for sigma, we have to write here DF. DF is degree of freedom is 229. 229. That is 2, regression coefficient is 2. And C, if we want R squared values, so here R dot squared. So we have got the value of R square. So this way, if we want F statistic adjusted R square, we have to write adjusted at ADJ R squared. ADJ adjusted ADJ dot R squared. So we have got adjusted R square. Similarly, if we want F statistic, so F statistic, F statistic. So this is the value of F statistic. The value is 419. Numerator degree of freedom is 1 and denominator degree of freedom is 29. So this way we can extract many information from a see, I have written these things. There are a number of other things we can get. Say for example, coefficient M1, see, if we want summary of coefficients, we can get, this is the summary of coefficients. Then if we need residual degree of freedom, it is these are the residuals, and sum of square residuals, it is sum square residuals. So this is, and this is nothing but deviance. Actually, sum of square residuals is the term which is especially mentioned when error distribution is normal. But if error is not normal, then what should be the term? So that's why in generalized linear model, when Nelder and Wedderburn in 1972, they developed generalized linear model, and they have written a great book by Mac Kudog and John Nelder, that is Generalized Linear Models, published by CRC Press. So, in that book, they have used the term deviance. Deviance is nothing but a generalization of residual sum of square for other models too. So, that is the term deviance. So, either you say sum of square residuals or you just type deviance. Deviance is they are same. So, now model matrix, X matrix, model matrix I have already told you model matrix X is equal to model dot matrix. See, this is the model matrix. This is the model matrix. See, we have just selected first to third row and 31st row. Otherwise, if we just print x1, so here model dot matrix is a function. Model dot matrix, here M1. So, it is nothing but capital X matrix. Capital X matrix, this is view capital X. See, this is the model matrix. This is the model matrix. This is the first column. This is the first column of intercept 1, 1, 1 and then girth. So, this is model matrix. And model matrix I have already explained to you. Just I will go on. See, y is equal to x beta plus e. This is the general linear model, and this matrix is known as model matrix. This matrix is known as model matrix. So, we can extract this matrix by using the function model dot matrix. We can extract these coefficients by using the coef function. So, we will go to the R commands. Yes, model matrix. Now, MS residual, it is nothing but MS residual is nothing but C deviance, that is the residual sum of square divided by the degree of freedom. So, if we talk of df dot residual of M1, it is what? Is it 29? Because df residual is nothing but n minus the number of columns in X matrix. So, there are 2 columns and the observations are 31 minus 2 columns. So, degree of freedom df residual is 29. So, that way we can get information about df residual. This is the deviance, and this is nothing but deviance is nothing but actually it is nothing but residual sum of square divided by the degree of freedom. See, if we talk of sum, it is nothing but sum residuals M1 and its square, sum of square residuals divided by the degree of freedom, and that is 29. So it is same value 18.07, and that is nothing but deviance divided by df residual. So this is the explanation of deviance. Now we can talk about sum of square deviance. Yes, summary M1 sigma I have already explained. No, this is the square root of deviance M1 divided by df residual. Its square root is nothing but the value of sigma. And if we want to print sigma, we can extract sigma with summary M1 sigma. So this is the interpretation of. To get the fitted values x beta hat, actually fitted values are nothing but, see, if y is equal to x beta is, then y hat is the fitted values, and this is nothing but x beta hat. So x beta hat is termed as fitted values. So we can extract them. We can extract fitted values x beta hat. We can extract them using x beta hat is equal to fitted M1. So these are the fitted values. We can print the x beta hat, control 2, x underscore beta hat. So these, say for example, the last 31st fitted value is 67.41, and if we write predict M1, predict is more general, so the last value is 67.41. So here if we are using the same predictor, then it gives predict, and the predict is predict. Then variance covariance matrix of beta 1. Actually, what is variance covariance matrix? That I would like to explain. See, if we fit the model y is equal to x beta plus e, then beta hat is equal to x transpose x inverse into x transpose y. Now, what is variance of beta hat? Variance of beta hat is nothing but it is x transpose x inverse into sigma square, and if we put hat here, we have to put hat here. So this is known as variance covariance matrix of beta hat, and this information can be extracted by using the function VCOV of M1. So that we have used. See, VCOV. So we have used the function control 1. See, to get variance covariance matrix of beta hat, it is VCOV M1, and it is this. This is the variance covariance matrix of beta hat. So VCOV. Now I shall talk about centered form of simple linear regression model. So I will go in the PDF. See, centered form of simple linear regression model. See, if we fit a model y is equal to beta naught plus beta 1 x plus error, This is known as simple linear regression model. But if we fit y is equal to beta naught plus beta 1 into x minus mean of x plus error, then this is known as centered form of linear regression model. Then this is known as centered form of linear regression model. This centering plays an important role in estimation. It's called centered form of simple linear regression model. Note that in this form, beta 1 remains same, beta 1 hat remains same, but beta naught is equal to y bar in this format. Moreover, xi is replaced by xi minus c. Here xi, this whole can be treated as xi. So xi is replaced with xi minus x bar, that is nothing but x minus x mean x, and call SLR2 as argument. Similar changes are required in LM to implement this. We shall make use of transform function for this data manipulation. Following set of commands will make these things more clear. See, what we are trying to do, example trees, use the function transform to transform the variable d1 is equal to trees, and then we are getting a transform because we want to keep d1 is equal to tree, and then we want changes. So d1 transform d1 is this data object, and girth dot c we are adding a new variable, and that is nothing but girth minus mean girth. So it is nothing but x minus x bar. So we are adding girth dot c, and this is the result. Girth dot c. If you use this command, this is the result. And then fit a centered form of the model LM is equal to girth versus volume versus girth dot c, and then we can have the results. Here intercept is 30 and there it was minus something. So here beta 1 is same, beta 1 is 5.06, whereas when we fit LM volume versus girth, not girth dot c, it is minus 36. It is minus 36. So actually, when we will go, just I would like to explain these things using the commands. See, we are using transform. So first we are writing d1 is equal to trees. So d1 is nothing but trees data. It is trees data. Names trees, or names, and then head. Head is the trees data. Head is trees. Head is trees, and d1 is also trees. So we are assigning d1, and then we are making use of the transform so that d1 is equal to transform, and the first object is d1, and then we are adding a new variable in d1, and that is girth dot c, and that is nothing but it is girth minus mean of girth. So that way, now if we keep head D1. Earlier D1 was having only volume girth, but here besides girth it has girth.c. So this data is there, girth.c, centered form. It is girth is equal to, girth has been replaced by girth minus mean of girth. So now if we fit this data to fit, now M1 is equal to Lm volume modeled as girth c and data is equal to D1. So summary M1 we have got the result here. Actually, if we fit M11 is equal to Lm volume tilde girth, not girth.c, we are using girth, and data is equal to, say D1 or trees, both you can have, and then we put the summary M11. See what is the change here. We are having the intercept beta naught is equal to minus 36, whereas beta 1 girth is 5.066 and here also 5.066, but intercept here in centered form is 30.17 and here it is minus 35, because of the reason that in centered form actually if we are fitting y is equal to beta naught plus beta 1 x plus error, then beta naught hat is equal to y bar minus beta 1 hat into x bar. Whereas if we fit y is equal to beta naught plus beta 1 x minus x bar plus error, then beta naught hat is equal to simply y bar. So this is the change, but beta 1 here and here both are same, they don't change. Beta 1 in both the cases it is 5.06, here it is 5.06, but beta naught here is minus 36.9435, but here it is just mean and it is nothing but 30 point something, it is mean of y. So this is the change. Besides that, there are some other advantages, and that I will continue in my next lecture, that what is the advantage, other advantages, how we shall talk about covariance matrix, and that I will talk tomorrow.